In this video, I want to show you why a proof by contradiction works. To do this, I need to establish a few facts. The first fact that I need to establish is that the negation of P implies Q is logically equivalent. Remember that logically equivalent, this is equals for logic, otherwise known as the same as, like equals is, right? That the negation of P implies Q is the same as P and not Q. To do this, I'm going to do this in two steps. Step one is I'm going to use a truth table to show you that P implies Q is logically equivalent to not P or Q. So let me show you that. Okay, P, Q, not P. P implies Q, not P or Q. Okay, the negation of P, this will give us false, false, true, true. P implies Q, straight definition here. We have false only in the case where P is true and Q is false, and true everywhere else. And now for this one here, we're looking at the OR of not P and Q. Okay, so for the first row, we have true or false. That's true. For the second row, we have false or false. That's false. For the third row, we have true or true. That's true. And for the final or fourth row, we have false or true, which is true. And so you see here that we have the same truth values, or the same exact columns, no matter what truth values we pick. So these are in fact logically equivalent. Okay, so now we've proven that fact with this truth table. All right, so now I can use De Morgan's law. So the negation of P implies Q. Right, so it's like I'm applying a negative to both sides in this, but I'm actually applying a negation. Not quite the same thing. So applying the negation to both sides, we have now using De Morgan's law, this is not P and not Q. This is De Morgan. De Morgan allows us to make this equivalence. Now remember, not P is P. So what we've established is that through a string of equivalences, logical equivalences, that not P implies Q is equivalent to P and not Q. All right, so that's the first thing we needed to establish. The second thing that we need to establish is that all mathematical statements are either true or false. Okay. Now we don't really need to establish this. This we know, all right? This is something that you can assume to be true, because establishing this is rather difficult. All right, all math statements are true or false. All math statements are true or false. Okay, so what does this mean? So what this means is that, so if it were the case that if P is false, then the negation of P is true. And if P is true, then not P is false. That's all we're saying there. Okay, so now let's see why contradiction works. Now remember that what we're trying to do. We want to prove that, so what we want to prove that P implies Q is true. So we want this to be true. That's what we want. We want to prove that P implies Q is true. Now, so with a proof by contradiction, what we do is we say, well, let's suppose P implies Q is false. Right, well, if P implies Q is false, then because all mathematical statements are either true or false, then we know that the negation of P implies Q must be true. Right, this follows from 2. Right, so we want P implies Q to be true. And we say, well, let's see what happens if it's false. Well, if it's false, let's see what happens if it's false. Well, if it's false, then its negation must be true. That's because all math statements are either true or false. Now, from 1, we know that the negation of P implies Q is P and not Q. Now comes the proof part. So now think of this ... as I'm writing some proof, right? And I come up with, I find a contradiction. Now what does that mean? Well, that must mean that our original supposition, the thing that we're supposing is false, right? Our assumption that P implies Q is false is a false assumption. So it's false that P implies Q is false. Well, if it's false that P implies Q is false, then it must be that P implies Q is true. And that's why a proof by contradiction works. So the idea, to go over this again, is we want P implies Q to be true. Well, we say, okay, well, let's see what happens if it's false. Well, if it's false, then its negation must be true because all math statements are either true or false. So if one statement is false, then its negation must be true. Now, we've already shown that these two statements are logically equivalent. So what we really do in a proof by contradiction is we just say, well, suppose P and not Q. Usually a proof by contradiction starts right there. We say, suppose P and not Q. We find a contradiction. And so this tells us that P implies Q being false is false. So it's false that P implies Q is false. So then it must be that P implies Q is true.